Good morning, everyone. Good afternoon, everyone, depending upon where you're located. I'm Ira Feldman, and I'm the Executive Director of MEPTEC. Welcome to our Semiconductor Industry Speaker Series that we co-produce with IMAPS. We welcome you to this month's webinar, so thank you for attending. Some brief introductory remarks here. We have some upcoming events. Our next Semiconductor Industry Speaker Series event will be on June 17th at 11:30 a.m. Pacific time. Stephen Rothrock from AT-Reg will talk about the US-China trade war. And then Chris Barrett from Insight SIP will be talking about miniature multi-mode SIP modules with integrated antennas. And then we're very excited that on July 15th, Jan Vardaman will be joining us with a global market update and her view of the world. And then the next speaker series event will be on August 12th. So please put these on your calendar. As soon as the registration is available, we will send out email and post links on our website. So please join us for these webinars, all great speakers and great programs. Talking about great programs, on Wednesday, September 16th, we have the Known Good Die workshop scheduled for Semi headquarters. We're optimistic that we will be able to hold this event on this postponed date, but we have a great program starting with David Greenlaw from NVIDIA giving the keynote, technical presentations from Cisco, Advantest, Synopsys, Mullbauer, FormFactors, and others. Registration will be reopening shortly, and it will be discounted through August 1st. And we will post all the updated details on knowngooddieworkshop.org. The abstracts and speaker information is there. We'll update the other logistics as we get closer. So please put that on your calendar also. Now it is my pleasure to introduce our first presenter, Sooyong Kim, will be presenting on multidisciplinary simulation for 2.5D 3D IC co-design. Sooyong Kim is the Senior Product Manager responsible for 3D IC and chip package system multi-physics solutions at ANSYS. He has over 20 years of experience in the EDA industry with concentration on power integrity, reliability analysis, and design methodologies. He joined ANSYS through its acquisition of Apache Design Solutions, and before that he had where he had held various positions in operations and customer success. Prior to that, he was with Cadence, and he received his BS and MS degrees in electrical engineering from Rensselaer Polytechnic Institute. So we welcome Sooyong Kim. So let you take the screen, Sooyong, and welcome.
Hi, everyone. My name is Sooyong Kim, and I'm currently managing products in 3D IC chip pack system, Multiphysics, and ANSYS. Thanks for joining today's talk about the multidisciplinary simulation for 2.5D and 3D IC co-design. My background is more from the chip design side. As a chip designer's point of view, hopefully today I will discuss what are the challenges in 2.5D and 3D IC with the new challenges coming in. More previously was on the off-chip side, including those the technology methodologies that is being they're currently being incorporated into the chip designs as well. So the evolution of a chip design has been going for 40 years, starting from 1980s, right? In the beginning, the designer was required to make the chip only to function, right? Hence, only function simulation or testing need to be performed, and the designers were okay with that, right? As the design requirement is more challenging and the technology advanced, more and more domains of testing need to be considered. as the chip design advanced to smaller and smaller following the Moore's law. And from the functional verification to the timing and the power and reliability due to the power and thermal impact due to the power. And the emission of electromagnetic waves makes the components to malfunction because of the very small factor of the design and very high power consumption of the components. And the complexity of the chip design now moving into so-called 2.5D or the 3D IC designs. And where now customers looking at the much more challenges, not only electrically, also electrothermal. And on top of the electrothermal, we're looking at the mechanical point of view as well. So that is different demands, and they're more challenging.
So Sooyong, also want to point out to the audience that they can ask questions in the Q&A tool, and I'll ask you at the right place. But want to be clear, you're focusing on the design side, but not the manufacturing side, like the computational lithography and the physics involved in that, correct?
Yes, yeah. That is correct.
Okay.
So moving from the single die to the multi-die designer's point of view, what does it mean to them, right? Each die can be a noise source of other die. And then also those dies are very close to each other. And being able to understand the both chip data as being like previous depth and lab, GDS, those are different input files, as well as all surrounding data. Like all the air gaps or soldables, the micro bumps, the copper fillers, and so on. And understanding those surrounding data very well is also very important. And being able to simulate multiple dies and all surrounding components at the same time for multidisciplinary domains is crucial, moving to the multi-die configuration. So electrothermal issue, first of all, for the 2.5, is at the core of making sure the product's reliability and functional integrity over a very long time. So in 2020, we do see that majorities of our customers are either already taped out 2.5D designs already, or have a plan to have a 2.5 design in 2020. There are many interposer materials used or tried commercially or in research in the industry. And it has glass and silicon and organic. There are 3 different types. As we can see, the glass shown mostly green in terms of characteristics. But while the glass is a more attractive material, but it is not readily supported by pure play foundries such as the TSMC or the Samsung. 80% of what we see in the market is the silicon interposer. So hence, being able to handle silicon data for the interposer was one of the key areas in the currently very hot 2.5D design. The 2.5 interposer is increasing. The size of that is, these days, you will see HBMs, 4 HBMs typically in the surrounding areas of SoC, and that interposer is connecting those each other. The number of HBM and on the speed of HBM increases as well. And the interposer designs with the correct way is actually one of the successful the conditions that you have to satisfy. So there are 2 things that I want to point out, that in order to make this 2.5D or 3D IC design successful, we learned it is important to look at all dies and all surrounding components accurately. Is very crucial for successful multi-die integration. So what the core technologies that the EDA has to make these multiple die integration successful, the ANSYS that has complete coverage of multi-scale and multiphysics in the simulations from nanometer to the centimeters, and power and signal thermal ESD to mechanical, and from RTL design level to the cell level or die level, and also package, board, and system level altogether, right? The comprehensive coverage of multi-scale and multiphysics is a key to make the multi-die tape out successful. So also, you have to think about the ecosystem. So ecosystem coverage is very important, from analog company to digital company, and also those analog and digital IP companies to the SoC company and package company. Finally, working with the tier one company through seamless modeling techniques to convey the design data from one company to the other. And for the next level of a simulation and verification, it is important to provide modeling techniques that can fit for various applications. And ANSYS provides a comprehensive list of modeling techniques for that. If you notice that at the bottom, you will have many different type of modeling techniques for different purposes. From IP to SoC, there are modeling techniques, and also SoC to the package, there are modeling techniques. There also from package to the SoC, there are other modeling techniques that we need to use and create models and create this ecosystem between, right? Make these designers seamlessly not losing any data when they do the verification or simulation. So I want to touch up a little bit on like what are the challenges and what are the requests from the customer. Typically, what we these days what we get on 3 different categories. I mean, there are more. There are like other topics, EMIs or ESD or cybersecurity and so on. I can talk about later on those topics, but these are the main ones, and I want to cover those first. Power integrity, electrothermal, mechanical, and then power induced signal integrity. So when you look at the system aware, the chip, the 3D IC PI analysis flow, so these are very typical, the layout. So HBMs are there, and multiple HBMs or SoC in interposer package together, right? So when customers are verifying the power integrity in the chip side and 3D IC and 3D and 2.5 3D IC, having entire entities must. But full data, having the full data, full layouts is actually is difficult, right? The because it has a lot of transistors, right? So, and having the entire network all together in one session is very challenging. So this is one of the examples that I gave you. When we have some full layouts from this customer, this happens to be like 4 HBMs plus 1 SoC. Typically, we are looking at multi-billion node counts, and node counts meaning like RLC network counts when you convert this the entire circuit into the RLC network. And typically, I see more than 100K, and a few years later, I'm looking at maybe billion number of a bump count. I'm talking about the connection point between one component to the other. So being able to take entire design of a full layout of dies plus a package, as well as the being able to be able to handle this so many the interfaces in between. Having the co-simulation or coupling between the components is very important and very crucial for successful verification of this PI. So typical, I mean, this one, there's one example. This one was around 5 billion node counts. The runtime was around 5 hours, but the computing resource that needs to solve this is humongous. These days, we are looking at thousands of cores, 2,000 of cores easily to solve this kind of verification. This is one example that is direct, yes.
So when, unlike traditional FEA where you can rely on symmetry, because unless it's the same die in multiple places, does the multi-physics, can you rely on any symmetry to reduce the computational load, or do you basically have to simulate the entire structure?
It depends on the computing resources that customer has. So far, we didn't have any limitation for how much we can solve, but depends on how many cores or CPUs available for, and the memories for, and the disk spaces for the customers has. We are talking about the terabytes here, right? Terabytes of memory, terabytes of disk spaces here. So not everyone has that kind of affordability, right, for the IT structure point of view. So we also provide a way of reducing the models as well. So we call the different model techniques for the to take care of the coupling between the dies and the package. We can the customer can choose to model it and make a black box, but maintaining this coupling impact though, right, from die to the other. So one example here, one can create some kind of die model. Some cases, customer does not even have any layouts for what HBM, for example, which is very typical. Even that case, we can create some kind of die model that can use it as a coupling. And we also in the system level, typically they cannot really offer to have this so much of LSC network when they do the SPICE simulation. In that case, we can also model this full layout with a very simple SPICE stack, and then make them to be able to simulate it, and then make this model to be more adequate for the system simulations as well. Because typically when we take out the PI in the die level, we are talking about nanoseconds. But when the system level, it goes to the system, it's much longer simulation that are needed, even more so in a thermal, right? So we are actually giving you a lot of different techniques that people can model it with much longer, with the different targets and different scenarios as well. So that's where our techniques comes in, and it is proven over and over with multiple silicon tape out. We were actually doing the silicon correlation with that too. So there are customers, until they get like the final confirmation or the confidence using this, we've been going through a lot of challenges with this modeling techniques as well. Okay, so there are other techniques like you suggested, modeling techniques are there, right? So, and when you look at the power integrated, there are challenges and efficiency. They are looking at the efficiency of the power and the power delivery network, how those are well designed. But when you look at the designs, they will have to look at the entire power delivery network entirely. Right. So, and then not only from the chip side, also they will have to look at the system side as well. So the different techniques of modeling is very, very important because of that. Yeah. And then looking into the thermal side, I mean, I just said that there are different techniques of the modeling, and we actually provide something called the CTM, which is the thermal model for the chip. And it not only includes the power density, it's just not top power density, also thermal dependent power density. And also material information, so all layer by layer, we keep those information and create a CTM. And then when you talk about thermal, there are two thermal components within the die. And there is a cell feed, which is due to the dual heating of the wire itself, and plus the global system level of thermal. So combine those two are the complete thermal profile. So unless we actually combine those, we can't really predict correct the temperature within the die. So we have to consider those two together, and then we have a closed loop between the thermal to power the relationship. So while we are doing it, we have to create this correct model techniques, and so that it's proper for the thermal analysis that which is a very long time, and considering all the mature information underneath, not just the power. And people are demanding more and more detailed analysis, not only just the system power only for one power number, because of various reasons. In the beginning of this design, these days they will have to do this prototyping. So in the architecting this 2.5 3D IC, they will have to decide the material, how many layers there need to be, how many bumps there need to be, how many TSV, TDVs need to be there, right? So in order to decide those, you need those very detailed analysis upfront. And when you do that, I mean, you need to maintain all those components, and just to be adequately decide to those decision points for upfront in the front end. So we provide this prototyping as well as the sign-off solutions at the same time. Having been able to look at the all details, this one basically, this example has 4 different HBM in it, and plus 1 SoC, board plus package, full detail. So we look at every layer, you get the temperature profile in every location with this. So that's the details what we're looking at these days. And then there are other stuff like thermal is also mechanical. So it has to be, we have to know the mechanical stress point of view, this thermal, how much thermal is impact. Now, because the geometry is complex, Now they want to know this expansion, this coefficient is actually from the different components of silicon is actually the same, so that it expands the same, right? So the work PG, you have to take a look at it. And also the current densities looking at is humongous these days through this one bump, right? So you will have to take care of the joule heating because of that. So there are actually, I see many failures from the customers where there is an interface is there clustered currents are going on. So making sure, so because we are making sure that from the power point of view, the thermal side, it is related to the current that is flowing through, and it estimate the current exactly. I'm talking about transient current, waveform as well. So and it is very important. And otherwise you can't get the believable result with that. So joule heating, self-feed inside the die, power dissipations, and being able to simulate it all together, right? So that's the key for successful thermal analysis and the mechanical, and we're looking at the same time. HBM SI, it's now crucial to look at these SI, typically was off-chip guys doing it. Now you're looking at the silicon, interposed silicon, right? So now you're looking at the channel models of like thousands of channels at the same time, but it is very close to the HBM, like a memory. It is and actually HBM is actually power, the power noise is HBM is very susceptible to the power noises. So being able to also have a way of doing the SI with the power noise included in it is very important. And the capacity is also very important because of that. And now you're looking at the HBM2 or HBM2E. Right now you're looking at 2 giga BPS per pin for the bandwidth point of view. And you're looking at the HBM3 now is coming up like 2.7 giga BPS per pin. So that in order to serve this the bandwidth, not only the capacity is very, very challenging, and now the equalizer is coming in, and for the serial type of the buses and so on, and also being able to analyze the channels at the same time is very challenging. And because of that, the channel model that we do better be very accurate, right? So, and the component side of channel model as well as considering different noise into the channel model is very important. So we actually created the platform in here. Now it's easy to connect those different components with the line here. As is one of the example. We try to make it very easy to use, but the key component here is not just the ease of use, it's actually the accuracy that we need to bring in. And also the HBM, typically you're looking at the power and noise as well. So the modeling techniques of I/O that produces the power induced noise into the IC is very, very important. So and looking at this, the virtual, the compliance kit, that the report, we actually automatically creates a pass-fail. And this eye diagram shows that depending on the PI noise, the impact of eye diagram is changing like this, right? So we actually did the 512 channel at the same time, and this is HBM2E. So looking at the SI challenges, there are like bandwidth increasing, and we have to meet this very fast changing the standard requirement, and AMI is another one that's for the series, and then extraction of a channel model, the accuracy of the channel model is very, very crucial. And we have a lot of different techniques for to doing that, and we continue to invest more to make this more accurate and capacity to support these capacities as well. Okay, so I think I have done in here. If you have any questions, I think I went too fast.
You covered a lot of material, and let's see if there's particular questions from the audience, but while they're putting their questions in the Q&A tool, I had a question with, you're taking multiple domains in physics. Is one of them more computationally intense? Obviously, you need to do all at once to get a valid answer because they're interrelated, but does simulation of certain things take more computational resources than others that significantly make these jobs blow up and scale, or do they all sort of stretch it at sort of the same rate? So
the computational point of view, if you go more to the chip side, it demands more computation resource point of view. So we typically need like 1,000 processors and terabytes of memory. But when you go to the system side, it is different question. But it's not as much as what it would be demanded in the die side though, right? But what the industry is trying to do is we combine those together, and then use these techniques that we've been trying this in semiconductor side, the die side, because we've been distributed computing, we call the big data system. So there's a abrupt changes in the computer science area in the EDA industry as well. So we are trying to apply this kind of different big data platform into all the rest of it as well for the multiphysics point of view. So it's gradually happening. It takes time to incorporate all things that we've been doing in the SPICE, for example, right, into the big data system. It's going on, right, but it will take some time.
Okay, and so we got some questions in here. Well, one was on timing. How do you do the timing analysis across multiple die or through the interposer? I mean, how is that handled briefly? Because I'm sure it's a pretty complex question based upon who asked it. So,
yeah.
And
so
actually,
it depends on
Herb asked it. So, well, you know, so.
Yeah, it depends on the stages that where you are at as well, right? So in the beginning, typically in 2.5 3D-IC, they want to actually start the make sure the interfaces, the cross-domain interface is actually done first. And then assuming that actually some kind of zero numbers in the H blocks and so on. So we create, the people are making sure, we have to make sure that the SDC file or the constraint files is actually from top down. And then they actually resolve that each individual chiplet or chips with those front information available already. So that's why now there's even power and more so timing as well. The top-down approach of prototyping for the timing information included is also important. Yeah. And of course, I mean, we want to reveal everything from all the way, right, when you do the simulation. But I mean, it's seldom all those information is varying, and it is only available at the very end, right? So that is different challenge, right? Okay.
Got it. Okay, good. Let's see. Actually, I think this is Professor Sumaraman. So Suresh is asking, can you talk about an example how you're using, you know, people are using it in terms of the number of chips and anybody who's doing chiplet-based work, or is it just all chips and you know, interposers and stacks, or have people doing chiplet work yet?
Yeah, but these days, most popular one is 2.5. So looking at the size of the interposer, so interposer with SoC and HBM are most popular style at this point. There are true 3D-IC for the different applications, like the image sensors, and also like AI chips that are in different areas as well. But immersely, the need right for the 2.5 with the interposer with the HBMs are most popular styles these days.
Yeah, but so no chiplet work yet, where you
there are. I mean,
starting.
there are different styles and too, right? There are chiplet work there ongoing as well. But most popular, I'm talking about the most popular one. Yeah.
Okay, got it. Wow, you got a lot of questions here. Okay, so so this is for people who want to know more. You have the ANSYS Learning Hub. So the topics you covered here, are they in the Learning Hub, or is it best if people reach
the Learning
you?
Hub. I mean, I'm typically very behind putting the latest material, but I mean, I'm in the refreshing step right now, and I'm refreshing all the materials as well. But yeah, there are a lot of materials already there, and 2.5 materials there too. Yeah.
Okay, got it. On a specific question on slide 17, it's asking the channel simulation you have, what type of inputs are needed from the power network to account for power noise?
There are two different cases. One is you can have a full layout and then create this noise model. That's one way. There's the other way, without anything, you can estimate the like a purport power and then create models and inject it in this way in the here.
So
this one we actually without anything.
Right.
Yeah, assumptions. Yes. So we didn't have a layout in this case, which is a typical case. Customer doesn't get the full layout from the vendors. So we actually, in this case, actually we created this model without anything. Yeah.
Got it. Okay. Oh, so this goes back to the scaling. You know, you at the beginning you talked about the scale of the different levels, the nano, micro, you know, milli scale. Are all the simulations run at the same scale and same accuracy, or when you combine them, or does how does it partition it? How does it make it efficient and computationally, and when you're putting it all together?
So that's why it is important to apply different techniques for different applications, right? For thermal, for PI purpose, SI purpose, all different. And then we create different models and with the different scales and different accuracy requirement for that region, right? And then typically the sources are from the power analysis, like the individual dies power and from the RTL level estimations. And from that on, we model it because we know full detail upfront in the chip side, right? So we can actually increase the complexity of that from the chip side first, and then gradually simplify it, right? So that's usually how it goes.
Okay, got it. And let's see if there's any. One last question. When you simulate the thermomechanical stress simulation, such as temperature cycle, for let's say 2.5D or 3D structure, how good is the correlation to actual test parts? Are you being able to close that loop? You know, where you build it.
Yeah, we constantly work with the customer. Yeah. So only way is to verify with the customer data. So we work with various foundries, which has measurement data, right? So that is important to make sure whatever we simulate actually correlates with what foundries is seeing in the lab. Yeah, so that's why it is important to have the experience, right? So the multiple tape outs, you should have that experience in order to come up with a good simulation. Yeah.
Are we 50% accurate? Not high 90s? I mean,
that question I often get it. I don't have a good number for, but typically few degrees is what I'm looking at. Few degrees. Okay. Yeah. System simulator guys are all good with a few degrees. Yeah.
So okay, and when it's really off, you can say it must have been your input data versus the simulation.
If it is 80 versus 120, it's always the input problem. but yeah, anyway, yeah, okay. Not a problem. Yeah.
Okay. So there's a bunch of other questions that we're not going to have time to get to, but I will send them to you, and some of them have names on them, so then you can reach out to those people, or those people can reach out to you and follow up. So I thank you very much, Sooyong.